Welcome to your IELTS listening practice from Spinta.org. This is a mini-test designed to help you practice a specific section of the exam and improve your confidence. The recording will be played one time only, just like in the official test. Let's begin.
Good morning, everyone. Today, we will explore a fascinating subject in structural biology: enzyme catalysis mechanisms. This topic is vital for understanding how biochemical reactions occur in our bodies and in various industrial applications. First, let's begin with the definition of enzymes. Enzymes are proteins that act as catalysts in biochemical reactions. This means they accelerate reactions by lowering the energy barrier required to initiate these reactions. One of the most critical aspects of enzymes is their active sites. The active site of an enzyme is a specific region where the substrate, which is the molecule upon which the enzyme acts, binds. Understanding the characteristics of active sites helps us comprehend how enzymes function efficiently. Now, how does the binding of substrates at the active site enhance the rate of reaction? When a substrate binds to the active site, it forms an enzyme-substrate complex. This complex is essential because it stabilizes the transition state, the point at which bonds are breaking and forming, thereby reducing the activation energy. Additionally, enzymes can provide an environment that is conducive to the reaction. They might bring substrates closer together, ensuring that they are in the right orientation to react. This results in an increased frequency of effective collisions among reacting molecules. Let's introduce a key concept: specificity. Enzymes exhibit a high degree of specificity, meaning that each enzyme typically catalyzes a particular reaction with only certain substrates. This specificity arises from the unique arrangement of amino acids that create the active site. For example, the enzyme lactase specifically catalyzes the hydrolysis of lactose into glucose and galactose. If we were to introduce a different substrate, such as sucrose, it would not be catalyzed by lactase because of the differences in molecular structure. Moreover, the environment around the enzyme also plays a crucial role in catalysis. Factors such as temperature and pH can significantly affect enzyme activity. Every enzyme has an optimal temperature and pH at which it operates most effectively. Deviations from these optimum conditions can lead to decreased activity due to denaturation. Now let's discuss how we measure enzyme activity. One common method is to monitor the rate of product formation over time. For example, if we consider an enzyme-catalyzed reaction where the substrate concentration is increased, the initial rate of reaction will also increase up to a certain point. This phenomenon is captured by the Michaelis-Menten kinetics. Michaelis-Menten kinetics provide a mathematical model to describe the rate of enzymatic reactions. According to this model, the rate of reaction reaches its maximum value as the substrate concentration increases, showing that there is a saturation point at which all active sites are filled. As we move forward, I want to address the importance of enzyme inhibitors. Inhibitors can decrease the activity of enzymes and are classified into competitive and non-competitive inhibitors. Competitive inhibitors resemble the substrate, competing for binding at the active site. On the other hand, non-competitive inhibitors bind to a different part of the enzyme, causing a change in shape that affects the active site. Say, for instance, in the case of HIV protease, a competitive inhibitor can be designed to mimic the substrate the enzyme normally acts on. This mechanism has been vital in developing treatments for HIV. Furthermore, the role of cofactors and coenzymes cannot be overlooked. These are non-protein molecules that assist enzymes in catalysis. For example, many enzymes require metal ions, such as magnesium or zinc, which assist in stabilizing the structure of enzymes or participating directly in the reaction. Coenzymes, which are organic molecules, also serve as carriers of chemical groups or electrons in various biochemical reactions. A classic example is coenzyme A, which is vital for the metabolism of fatty acids. As we summarize this lecture, we can reiterate that active sites are essential for enzyme function. facilitating the conversion of substrates to products while enhancing reaction rates. The specific structure of each enzyme's active site plays a vital role in determining its activity and specificity. In conclusion, enzymes are remarkable catalysts that have profound implications on biological processes, industrial applications, and therapeutic interventions. Understanding their mechanisms, especially how they bind substrates at the active sites and accelerate reaction rates, is fundamental in both structural biology and biochemistry. Thank you for your attention. I hope this lecture has provided insight into enzyme catalysis mechanisms, where the significance of active sites in reaction rate acceleration is both clear and compelling.
You have now completed the practice test. When you are ready for a full exam experience, visit us at Spinta.org. There you will find complete mock tests for all 4 skills: listening, reading, writing, and speaking. Our platform provides instant AI feedback for your speaking and writing tasks, along with an accurate prediction of your band score. Take control of your preparation at Spinta.org.